All right, we'll continue our discussion of Chapter 8, Sequences, by talking next about the limit of a sequence. You're already familiar with the concept of limits because we, of course, studied limits of functions in Calc 1. We'll now talk about, first of all, what do we mean by the limit of a sequence, and secondly, how does it compare to the idea of the limit of a function? So, a little vocabulary review. As the index increases, it's possible that our terms may approach a particular value, L. In this case, we say that the limit of the sequence is L, or that the sequence converges to L. And we might write something like this. The limit as n goes to infinity of the sequence an is L. All right, another possibility is maybe as the index increases, that is, as n goes to infinity, the terms may increase or decrease without bound, that is, become infinite in either the positive or negative direction. In that case, we would say that the sequence has no limit, or we say that it diverges. Okay? So, here's a couple of examples. This sequence, 1/2, 1/3, 1/4, 1/5, and so on, converges because all of the terms are getting closer and closer to 0. So we might say that converges to 0. The sequence 1, 2, 3, 4, 5, since it just keeps on getting bigger and bigger without bound, diverges. There's actually a third possibility. It's also a situation in which we say a sequence diverges. But that is, rather than approaching a single value, or even becoming unbounded, the terms of a sequence may sort of wander with or without a pattern. In this case, the sequence also has no limit, and we say that it diverges. So here's a simple example of what I'm talking about. Think about this sequence. Okay. It's not approaching any one value, right? It just keeps on going back and forth between +4 and -4, but it's not approaching either one of them permanently. It doesn't get unbounded. It doesn't get infinitely large or infinitely small. But because it kind of wanders without doing either of those things, in this case with a pattern, we say it diverges. All right, so ideas of sequences converging or diverging. The next question we want to discuss is, how do we find limits of sequences? And in order to answer that question, I want to talk about how the limit of a sequence, a sub n, is different from the limit of a function, f of x. Okay. Now a series, oops, sorry, that is a typo. That should say sequence. A sequence is always discrete. As opposed to a typical function, which is mostly continuous, right? We know we can have a point or two of discontinuity, but the majority of a function is usually continuous. Right? Let's take a look at a sequence and a related function. I'm going to look at the sequence, a sub n, in which the terms are all defined as 1 over n. And then I'm going to look at the function, f of x equals 1 over x. Okay. What's the difference between this one and this one, other than just the letter n versus the letter x? Well, the difference is, in a sequence, remember, we're thinking of n as going from, say, 1 to infinity, but it doesn't go through all of the fraction and decimal values. N is never 1/2 or 2 1/4 or 5.7. N becomes 1, and then 2, and then 3, and so on. So it's discrete. We only hit certain values of n. And if I were to start to write out that sequence, starting with n equals 1, 1 over 1 would be 1, and then I would jump to 1 over 2, 1 over 3, and 1 over 4, and so on. If I were to actually try to graph that sequence, what would it look like? Marked by quarters there on the y-axis. We'd have the point 1, 1, right? This is an n equal 1. And this is our n equal 2. So we'd have 2 1/2. And then our n equal 3. So I'd have 3 1/3. And then finally our n equal 4. So 4 1/4. And of course those y values would continue to get smaller. But notice we don't connect the dots like we typically do when we graph a function, right? These are the only specific values of n that the sequence takes on. The sequence is never equal to 1 1/2, so I'd have no point here for 1 1/2, and so on. Okay. This would be considered my n-axis, and these are the a sub n's. All right, what about the function y equals 1 over x? We all know what happens when we graph that, right? I could actually kind of almost think about the same idea. We'd still say, for example, when x is 1, 1 over 1 is 1. When y is 1, we would get 1/2. When x is 3, we would get 1/3. And when x is 4, we would get 1/4, and so on. But this time, we also have all of the values in between. We actually have a continuous function going up the y-axis there, since when x is 0, it gets infinitely large. So this time with the function, yes, x could be 1 1/2 or 3.4 or whatever. We've got our values of y for any possible value of x, not just the integers, like we do for a sequence. All right, how is their convergence related to one another? Because here's the thing. We have a lot of knowledge about how to find limits of functions, right? It'd be great if we could use those pieces that we already know about to predict the limits of the sequences. Unfortunately, it turns out we can't. Notice that if this whole function approaches 0, which this one will, right? There's a horizontal asymptote at 0. Then the individual points must also approach that horizontal asymptote at 0. So the limit of the function is going to be the same as the limit of the series. In this case, 0. So the theorem down below states that formally. If the sequence a sub n has explicit formula, a sub n equals some function of n, and the limit of the function f of x, same f here, is equal to L, then the limit of the sequence will also be L. So, we can use all of that knowledge that we've amassed about function limits and use them to calculate sequence limits. They will be the same. That means, of course, that limit laws also apply to sequences, just like they did to functions. Here are a few to remind yourselves of. Let's suppose that we have a sequence of terms a sub n, whose limit is a, and a sequence of terms b sub n, whose limit is b. Then, let's write down the limit theorems for each of these. The limit of the sum or difference, a sub n plus or minus b sub n, would just be the first limit, a, plus or minus the second limit, b. Constant multipliers can be pulled out of the limit. So we're just going to get c times this limit, which is what we were calling a. The limit of a product is the product of the limits. So the limit of the a sub n's, which is a, times the limit of the b sub n's, which is b. It's same with the quotients. Limit of the a sub n's, which is a, divided by the limit of the b sub n's, which is b. So all those things we could do with limits of functions, we now can do with limits of sequences. So we're going to get a chance to refresh our limit skills here. Let's go ahead and try to find the limit of each sequence. We'll go ahead and find it algebraically, and then I'm also going to show you how to generate a sequence graph on your calculator, right? Like the one I did here, where we graph the sequence, which the individual points. Your calculator can do that too, and I'll show you how to do that so that we can check our answers. All right, here we go. Our first sequence right here, and I'm going to say the limit of that sequence can be found by finding the limit of the function, letting x go to 0, or excuse me, go to infinity, of 2 to the x plus 2 plus 6 over 2 to the x. And again, I've changed from n's to x's because I've gone from the sequence to the function. That theorem on the previous page said the limits are going to be the same, and I know how to find this limit. Boy, I really got some mixed messaging here, though. Let's just make that a parenthesis. All right, in this case, I think breaking apart the fraction is going to be the way to go. If I make this two fractions, 2 to the x plus 2 over 2 to the x, plus 6 over 2 to the x, this first one I could just subtract the exponents, so x minus x will be 0, and I'll just end up with 2 squared. Two squared, of course, is 4, and as x becomes infinitely large, 2 to an infinitely large power is going to become infinitely large. And of course, a fraction, a constant value over infinity, is going to go to 0. So I'm just going to end up with 4 plus 0, or 4. Okay? That is not only the limit of the function, it's also the limit of the sequence. So let's see if we can see that graphically. On your calculator, go into your mode, right here next to the second function mode, right? And I've already got mine done. Normally, we leave our function or our calculator in function mode. That's what we've always done up till now. But I'm going to have you move this over to sequence mode. And when this is in sequence mode, if I hit y equal, it looks very different now than what you're used to. It says, let's just assume that we're going to start with our n minimum at 1, which is typically, right? We start with an n of 1. And then it asks me, what is u of n? That's just your a sub n is what we've been calling it. Same thing. So let's put that in there. We had 2 to the n plus 2. By the way, I'm getting the n just like I got the x, same exact button. Plus 6 over 2 to the n. I now want to graph this. Let's set a window. Again, if you just remember what we saw over here, right? I kind of had my window from like about -1 to 5 on the x-axis. We could go a little further. Maybe we'll go -1 to 10 on the x-axis. But everything's really small on the y. Everything's 1 or smaller, so I'm going to keep my y values pretty small. So I'm going to go 1 to 10 for the x's. And the x's and the n's are really the same thing. We'll start at 1 and we'll step by ones. So we're going to go 1, 2, 3, 4, 5, and so on. -1 to 10 for the x's with a scale of 1. And again, the y's are pretty small. Let's go with, oops, good grief. -1 to 2 with a scale of 1. There we go. And hit graph. All right, why am I not seeing these? Oh, good grief. I'm sorry, my y's were small, but not that small. The limit was going to be 4, right? I should have gone a little bit bigger on the y's. Let's try that one more time. In the window, I'm just going to go to my y-axis. Let's go a bit bigger. Let's go with a y max of 10. There we go. Now I can see it. So you can see we started out on the larger side, and then these sequence points get smaller and smaller, and they approach that horizontal asymptote at a y value or an a sub n value of 4. So I can definitely see that the limit of that sequence certainly looks like the 4 that I expected. All right, let's try another one. Same deal. I've got a sequence. I want the limit of the sequence, but I'm going to find that by calculating the limit of the function. So I'll make that 1 minus 4 over x to the x power. Now, you may remember this one. Anytime we have, in this case, that piece goes to 0, so this is 1 to the infinity. This is an indeterminate form, right? And when we have the exponential indeterminate form, this is the one where we're going to need to take a natural log. So let's call this the natural log of the limit. Actually, this is the limit first. Then I'll take the natural log. One step ahead of myself. This is our limit L. And now I'm going to take the natural log on both sides. There we go. Natural log on the left, natural log on the right. That, of course, allows me to bring this x down in front. And I no longer have an exponential form. Now, unfortunately, I still have an indeterminate form. What I have now is x is going to infinity, and this is the natural log of 1, which is 0. So I now have the infinity times 0 form. All right, the way we usually handle that, we try to create a fraction so that we can use L'Hopital's rule. So that's what we'll do here. I'm going to take this x, and I'm going to move it into the denominator as a 1 over x, the reciprocal. Notice if I did the invert and multiply, the x would come back on top, so that's the same thing. And now I can do L'Hopital's rule, because right now I've got the natural log of 1, which would be 0, over 1 over infinity, which is also 0, and 0 over 0 is a L'Hopital's rule form. So here we go. L'Hopital's rule, we do the derivatives, top and bottom. We will get on the top 1 over 1 minus 4 over x. And then for the chain rule, the derivative of the argument here would be 0 minus, and that's actually like a 4x to the negative first. Negative 4x to the negative first. So when I do my product rule here, or my power rule here, I would have a positive 4x to the minus 2. On the bottom, think of that as an x to the minus first. So I'd have negative 1 x to the minus 2. All right, that's some good news because I can now divide out the x minus 2's. And let's see, as x goes to infinity, I have 1 over 1 minus 4 over infinity times 4 divided by negative 1. This fraction goes to 0. So I've really just got 1 times 4 is 4, divided by negative 1 is negative 4. But remember, that is the natural log of the limit. So I would exponentiate both sides, and my actual limit is e to the negative 4th. A little more to that one. All right, let's try that out with a graph. We have got 1 minus 4 over n to the n power as our function. In the window, let's see, this one, I've done this one ahead just to make sure. This is a limit that's a little bit harder to reach. We're going to need a lot of terms to see it. So I'm actually going to go out 500 terms. We'll start at 1 and step, we don't have to do all 500, let's step by tens. So we'll let n be 10, 20, 30, 40, etc. until we get to 500. And I'm going to go with some pretty small numbers here. I'm going to go with negative 0.05 to positive 0.05 with a scale of 0.01. Those are my y's. Let's go do x's first. X's have to still go, they have to be like the n's. Those go from 1 to 500. Sorry about that. With steps of 10. Y's are the ones I want to be really small. Negative 0.05 to positive 0.05 with a step size of 0.01. And again, there was some trial and error that I did to figure out what worked well. This one takes a moment to graph, but we'll see it. You can start to see it form here. It's just really slow because this is a fairly complex function. Even the calculator takes a minute or two to do it. While it's doing this, by the way, on your calculator, if you just quickly plugged in, e to the negative 4th turns out to be about 0.018. So, if we were to trace this graph, watch what happens to those y's. 0.015, 0.016, 0.017, right? And notice how we're really leveling off on the actual appearance of the graph now. And we do eventually get really close. Notice 0.0179. And then we're finally going to hit just around 0.018, I think, right at the end here. Goes a little above that. That was, of course, a rounded off value. But you can see how we're really leveled off at about 0.018. So it does seem to be a reasonable value for the limit. All right, these next two show us some of the special issues that happen with an alternating sequence. Notice we've got the negative 1 to the n in both of these formulas. Okay. What I'm going to do, because it's really hard to evaluate the limit of a function with this in it, right? This really only works to alternate a sequence, not a continuous function. I'm going to kind of pull this out, and I'm only going to work with the rest of it. So I'm going to say, I know this is alternating. But then the rest of it, I'm going to think of as the limit as x goes to infinity. I'm going to make that an x squared. And on the bottom, 4x squared plus x minus 5. Notice we do have the indeterminate form, infinity over infinity, which means that I can use L'Hopital's rule to do the limit. That is going to give me, oh, I'm sorry, did I miscopy that? I did. That should have been an x cubed there. Let's fix that. There we go. So if I do the limit, on top, L'Hopital's rule takes the derivative and says 2x. On the bottom, it would be 12x squared plus 1. As x goes to infinity, still infinity over infinity. So I'm going to use L'Hopital's rule one more time. And this time the top just becomes 2. Derivative of the bottom would be 24x. And notice this is now 2 over infinity, or 0. Now I'm not quite done. I need to think back about the idea that this alternates. If you have a sequence that alternates as the terms approach 0, then what happens? Well, the whole sequence is going to approach 0. And the reason for that is that plus or minus 0 is still 0. So since negative 1 to the n, that's for the alternating now, times my limit of 0 is still 0 all the time, that is going to be the limit of my sequence. Right? I'm going to do the next one, and then we're going to graph them both. Right? So let's try this last one. Same issue. The negative 1 to the n really just says this is alternating. So I'm going to kind of pull that to the side for now and concentrate on the rest of it. I'll change it to function. Limit as x goes to infinity. So I can use all my great limit knowledge for functions. Function is x over x plus 1. And we are in the infinity over infinity case, meaning L'Hopital's rule does apply. So go ahead and do those derivatives. We just get 1 over 1, or 1. All right, now again, not done yet. I have to keep in mind this sequence was alternating. So I had a negative 1 to the n times that limit of 1. And notice this time we don't consistently approach the same value, right? Not like here, where the product was 0 no matter what. This is either going to be 1 or negative 1. 1 if n is an even number, and negative 1 if n is odd. Well, a sequence can't approach 2 different limits. A limit means all of the terms approach 1 value. So in this case, we would have to say that our sequence diverges. It's actually approaching 2 different values for even and odd values of n. So let's take a look. I'm going to graph this one first. We have our negative 1 to the n power times n squared. And the denominator was 4n cubed plus n minus 5. Right? We're expecting the limit to be 0 on this. As far as the window, I don't think we have to go all that far. I'm just going to go from 1 to 20. For my n's, we'll start at 1 and end at 20. start at 1 and our step size is 1. There we go. And then for the x's, we start at 1 and end at 20 with a scale of 1. And the y's, it's going to 0, so this will be somewhat small. Let's just try -1 to 1 for starters with a scale of maybe 0.1. And let's see what's going on here. Oh, there's a bad spot, isn't there? What makes that denominator equal to 0? We may have to avoid that. I'm just going to use my calculator to figure that out. I'm going to go into my Polynomial Solver. This was a third order equation. And everything should be fine there. I'm going to go to next. And let's see, my coefficients, we had 4n cubed. We have 0n squareds, 1n, and minus 5 equal to 0. And we want to solve that. And it looks like we've got a couple of imaginary solutions which aren't a problem, but one is a solution. So that's why it was giving me an error message back over here when I tried to graph. Right? So dividing by 0, when n is 1, that denominator is 0. So we can fix that. We just won't ask it for n equals 1. In our window, let's start with an n of 2. And we'll start our plot at 2 as well. That way we'll avoid that problem. We don't really care what happens for small n anyway. We want the limit as our n values are going to infinity. So eliminating that first point is no big deal. There, now it's much happier. And you can see, again, really small values. You can just barely see a couple of them down here, and they become close to 0 really fast, so they're hard to see. Maybe if I adjust my window a little bit. Let's go from -0.1 to 0.1. There, I can see it better now. Okay. And notice you can really clearly see the odd and the even powers, right? When we had even powers, those would be positive terms. So all of the even powered or even numbered n's are all up here. All of the odd values of n would have given negative numbers, and those are all down here. But notice that both sets approach 0. They're both squeezing in on that horizontal asymptote of y equals 0. So we were able to say that our limit was 0. Compare that to what happens in D. I'm going to go in and just change my function here. All right, there we go. And I don't think these are going to get small quite as fast. Let's, in our window, go back to the -1 to 1 for the y's. All right, you can see how we are approaching 1, but we're also approaching -1. Again, this would be the even values of n. This would be the odd values of n. But this time, they're not squeezing into the same value, right? Half of them are going to 1. The other half are going to -1, which is why we had to say that this sequence diverges. So with an alternating sequence, you can start by kind of ignoring the -1 to the end and just dealing with the rest. And then think about, hey, if it's -1 times whatever limit you got, the only one that's going to work out is 0. Any other number is going to have 2 different possibilities. All right, so there's some limits of sequences. There are a couple of theorems about limits of sequences that I want to talk about, two of them. The first one is just a really common type of sequence. It's called the geometric sequence, and it's got this form. A sub n equals a times r to the n, where a and r are just constants. If you have a sequence in that form, it's called a geometric sequence. A geometric sequence converges, and actually specifically it converges to 0, as long as r is between -1 and 1. That geometric sequence is going to diverge if r is greater than 1 or if r is less than 1. Now, technically speaking, we could actually put equals on these. It's just that if r is equal to 1, the sequence isn't very interesting, since 1 to any power is 1. So I'm going to put the equals on there, but kind of a boring sequence. Another way to write this is true if the absolute value of r is less than or equal to 1. And this would be the case where the absolute value of r is greater than 1. Let's look at a couple of examples. We'll kind of work them out numerically just so that you can see this theorem actually work. So let's start with the sequence 2 times -1/4 to the n power as n goes from 1 to infinity. So I would have 2 times -1/4 to the first, and then 2 times -1/4 squared, so on. And let's see, that would be -2/4 or -1/2. That's going to be -2/16 or -1/8. Positive, I'm sorry, when I square it's going to be a positive 1/8. That'll be a negative. And then 2/64 would be 1/32. And finally, that one's going to be positive. 2/256. That's 1/128. Just running the arithmetic. Notice that despite the fact that they alternate, ignoring the signs for the moment, these fractions definitely are getting closer and closer to 0, right? The denominators keep getting bigger, meaning the fraction keeps getting smaller. So how does that fit with our theorem? Well, we were in the case where our r value was -1/4. And notice that r value is indeed between plus and -1. And as advertised, my geometric sequence is converging to 0. Let's try one in the other case. Let's do one where the r value is, I'm going to go with greater than 1. I'm going to do 5 times 3/2 to the n, as n goes from 1 to infinity. All right, let's write out a few terms. N equals 1, 2, so on. And I just went ahead and I just used a calculator to get some decimal approximations to these, or actually I think they're exact decimals. just going to write them out for you. The first one you can see is 15 over 2, which is 7.5. And just plugging into the calculator, I got 11.25 for the next one. 16.875. And 25.3125. And I think it's fairly clear here that these numbers are just getting bigger and bigger. So this one diverges. As advertised, right? Diverges. In this case, our R was the 3/2. So definitely our R was bigger than 1. This one was smaller than 1. All right, so if you've got a geometric sequence, we're going to talk a lot more about those in the next section, by the way. There's a pretty easy rule to follow to determine whether they converge or diverge, one of our theorems. Here's our second theorem. It's called the Squeeze Theorem. And it says, suppose that we have 3 sequences, sequence of A's, B's, and C's. And let's also suppose that the B sub n's are in between the A sub n's and C sub n's for all n greater than some set finite value of n. If the limits of the A's and the C's are L, then the limit of the B's is going to be forced to be L as well. If you think about that one graphically, it's fairly easy to see. Let's say that that limiting value L is right here. And I know that the limit of the A's is L, so I'm just going to pretend that, let's just say these are the A's. I'm going to show them approaching L. And then the limit of the C's also has to approach L. So I'm going to put these up here since the C's are bigger than the A's. Now our B's have to stay between the A's and the C's. They can bop around a little bit, right? There's B1, let's say this is B2 and B3. But notice that in order to stay between the A's and the C's, the B's are going to have to stay really, really close to that horizontal asymptote, that limit of L as well. They're literally getting squeezed down in between the A's and the C's and ultimately have no choice but to approach L. So here's kind of a classic example of a squeeze theorem problem. I've got the limit of sine n over n plus 1 as n goes to infinity. Right? We know the sine function always gives us a result between -1 and +1. So what I could do is say this limit that I'm trying to find is in between. That numerator is in between -1 and +1. And I'm just going to leave the denominators the same, n plus 1. And these are actually both the limits as n goes to infinity. And I have to squeeze it in here. All right, and that's all because we know sine is between -1 and 1. Now let's think about these limits. This would be -1 over infinity, which is 0. And this is +1 over infinity, which is also 0. So the limit that I want is literally in between 0 and 0. And of course, the only thing in between 0 and 0 is 0. And I'm at the end of what I wanted to talk about, which is a good thing because it looks like I'm at the end of my ink. I have to get a new one before I make the next video. Okay. All right, we will come back next time and talk about an interesting theorem, a little bit more elaborate about limits of sequences, which is actually going to turn into a really valuable shortcut for us. So we'll do that next time.